Today, one of my students came across a great example of why you can't trust AI to know biochemistry. When asked how many turns of the TCA, so the citric acid cycle, would be needed to completely oxidize alpha-ketoglutarate, it said 1 turn. When, if you biochemistry it out, it's actually about 2.5. You see, alpha-ketoglutarate has 5 carbons. You lose 2 carbons per cycle, and so you're going to need 2.5 turns, so 1 partial turn to get to oxaloacetate, and then 2 full turns. So let's talk about how we could figure this out and how we could figure out how many turns for the TCA you would need for any intermediate that you put in, as well as the energetics that you get out of the process. So what you're looking at is basically part of an assignment I give my students where we do ATP accounting. This one's for the citric acid cycle, but we also do it for glycolysis, lipid metabolism, amino acid metabolism, you name it, in order to think kind of through different metabolic processes and interconversions. The basic idea is that you have for each process, you can count out how many NTP, so ATP, GTP, whatever, they're interchangeable. So you can think of them as equivalent. NADH, FADH2, and NADPH that you would generate or require directly. What you could then say, if you incorporate that you could use NADH or FADH2 in the electron transport chain for oxidative phosphorylation and get ATP from that, then you can figure out kind of how much energy you could potentially generate from the process or that you would need for the process. So here's the detailed version, then you just kind of like sum it up for a summary version. And you can combine processes in order to figure out the combined energetics for a certain pathway or interconversion. So for the citric acid cycle, let's think about what happens. So each turn of the cycle, if you start by putting in acetyl-CoA, that acetyl-CoA joins with oxaloacetate to make citrate. Now, when you put in acetyl-CoA, you're putting in 2 carbons. Oxaloacetate was 4 carbons. Now you have 6 carbons. And I'm so counting on the number of carbons. I'm so intentional about pointing out the number of carbons because each turn of the cycle, you're losing 2 carbons as CO2. CO2 is the most oxidized form of carbon you could have. So if you completely oxidize a molecule, what you're saying is you're converting all of the carbons to CO2. And the CO2, well, it can't be bound to anything else. The carbons can't be bound to anything but oxygen and CO2. And so you're basically getting rid of the carbons that way. And so you need to go 1 turn of the cycle for 2 carbons, and so if you have more than 2 carbons, you're going to need to go more than 1 turn of the cycle. If you have citrate, well, here you have 6 carbons, you're going to need to go 3 turns around. If you have something with 4 carbons, well, now you're going to have to go 2 turns. Well, at least 2 turns. Because if you start with somewhere other than starting with your citrate, well, now you're going to have a partial turn to get back, or then your oxaloacetate, you're going to have to a partial turn in order to get back to the oxaloacetate. When, as long as you have another acetyl-CoA you could bring in, you could then go around the cycle again and again, and you'd have to go again and again to get rid of that oxaloacetate. So for any intermediate, the first step is to identify the number of carbons that you need. And so that you have, and therefore that you need to then get rid of a CO2. Remembering that you're going to lose 2 per turn of the cycle. In our example, we're starting with alpha-ketoglutarate. Well, with alpha-ketoglutarate, we can see that we're going to have we have 5 carbons, 1, 2, 3, 4, 5, so we know that we're going to need about 2.5 turns of the cycle. We're going to need a partial turn in order to get to oxaloacetate, and then when we have oxaloacetate, we have 4 carbons left over, we're going to need 2 turns of the cycle. Per complete turn, what we have is we have the 1 NTP that we're generating. We generate 3 NADH, 1, 2, 3, and we generate 1 FADH2. If we take into account, so that's what we're directly generating. If we take into account the potential ATP we could get if we were to take these reducing equivalents through the electron transport chain in oxidative phosphorylation, if we say 2.5 per NADH, 3 times 2.5 is 7.5. If we say 1.5 per FADH2, 1 times 1.5 is 1.5. And so if we add those together, we get 9. Then that was basically from oxphos itself, and then we have that one that we had from the NTP, so a total of 10 potential ATP from this process, taking into account the oxidative phosphorylation. If you didn't take into account the oxidative phosphorylation, then you would only be generating 1 NTP. So really the bulk of the energy that you get from oxidizing molecules is through the oxidative phosphorylation, not through the citric acid cycle itself. So let's think about the catabolism of alpha-ketoglutarate, our example. We said it had 5 carbons, and we need about 2.5 turns. The about part is kind of important because depending on where you start, you're going to generate different things in the partial cycle. So if you were to put in isocitrate, well, that's the only case that you kind of get a full cycle's worth, because anything else, you're not going to get a full amount. When we start with alpha-ketoglutarate, we've already lost a CO2 and we've already generated an NADH. So we're not going to get this NADH that partial turn. Instead, we're only going to generate 2 NADH, and we're going to generate our FADH2 as well as our GTP, or ATP in different tissues or species. And so we have this 1 NTP, but now only 2 NADH, 1 FADH2. Now when we multiply things out, we get a potential of 7.5 instead of 10. So you can see that the NADHs, those are really energetically useful with the oxidative phosphorylation. So now we're back at oxaloacetate. And so now we have 4 carbons. So we need to go 2 full turns of the cycle. So we have 2 turns of the TCA, and we multiply that by the 1 NTP per cycle, the 3 NADH per cycle, and the 1 FADH2 per cycle. Therefore, we multiply those out, and we get a potential of 20 ATP from this process. We now need to add those together, and we figure out that we have 27.5 potential ATP from this process. So lots of potential energy, and most of it is coming from the oxidative phosphorylation. And importantly, the TCA is not really going to run unless your electron transport chain is running, because the NADH is going to build up and inhibit things. And so it's really important that the electron transport chain is going to be functioning. Okay. And so let's just kind of review. So we had 5 carbons. So figure out how many carbons you have. Figure out then how many turns of the cycle you need. Remembering that each turn of the cycle, you're going to lose 2 CO2. Then figure out basically where do you start? What do you generate in the partial turn to get to oxaloacetate? And then once you have oxaloacetate, you're going to have 2 more turns. So because you can only put in something into the cycle that's 4 carbons or more, like the things in the cycle are only 4 carbons or more, you're always going to have, if you put in the TCA intermediate, you're always going to have at least 2 turns of the cycle. If you put in oxaloacetate, you're only going to have 2 turns. If you put in anything else, you're going to have more than 2 turns. In the case of some of these, it's just going to be a partial turn. Like if you put in one of these 4 carbon compounds, you can still be generating reducing equivalents, but you're not going to have like carbons lost on this side of the cycle, but you will have to take into account these energetics. So it's really important to remember that you kind of have to get, in order to completely oxidize everything, what we're saying is that all of those carbons have to be lost to CO2. And that's going to mean that you have to go around the cycle as many times as it takes in order to lose all of those carbons as CO2. So it's not just, okay, well, we just oxidize it by just going back to the beginning. No, once you're at the beginning, then you have to go another whole 2 cycles. And so hope this helped you understand the energetics, and hope this helped provide a warning of why you cannot trust AI to know the answers to these questions, and why it's really important still that you are able to think things through. I encourage you to try to do the same for all of these different intermediates, and try to work out the energetics of other processes as well. Hope this helped.